Hello everybody, my name is Derek Dela Cruz, and this is my presentation on Chapter 22 of the AP Physics textbook, Current and Resistance. Let's get right into it. Now this chapter is all about current. Current is the motion of charges through a material, such as a wire. And the charge carriers are the charges that move in a current. And in the diagram, we see that current flows from the positive side to the negative side of the circuit. Current happens because of potential difference, and potential difference is the difference of electrical potential from two ends, such as a battery. That potential difference creates an electric field that drives a current in a wire. And it's important to note that current is also conserved in circuits. Current is the flow of positive charge. Now technically, current is the flow of electrons from the negative side to the positive side, but electrical engineers have decided to adapt to the positive charge flow convention, and it has stuck ever since. Current is defined as the change in charge divided by the change in time. Now the unit is 1 ampere, which is 1 coulomb per second. In a wire, there's sometimes something called a junction, which is a point where the wire branches to two different paths or more. And according to Kirchhoff's junction law, the sum of current going into the junction is equal to the sum of the current leaving the junction. Continuous light from a light bulb requires continuous current. A definition of a complete circuit is a circuit that allows the flow of charge in a continuous loop. In order to provide this continuous loop, batteries are used, and batteries are devices that consist of electrolytes, or chemicals, sandwiched between two electrodes, or ends. And the chemical reactions in the batteries create a charge escalator that lifts charges from the negative terminal to the positive terminal, and this creates a continuous current until the battery runs out of chemicals. The electromotive force, or EMF, is the potential difference established by a device, such as a battery, that actively separates charges, and that separation is its rating, and the unit of EMF is volts. Batteries are sources of potential difference, and in a circuit, since both ends of the wire are connected to the two ends of the battery, one can then deduct that the potential difference of the wire is equal to the potential difference of the battery. Resistance, with symbol R, is a measure of how hard it is to push charges through a wire. And some equations where resistance is used is current equals potential difference of a wire over resistance, which can also be rewritten as resistance equals the potential difference of the wire divided by current. And the unit of resistance is an ohm, which is just a volt over an ampere. And resistivity, with symbol P, represents the electrical properties of a material, which is pretty much resistance. And an equation where resistivity is used is resistance equals resistivity times length over cross-sectional area, the length and the area coming from the material itself. Ohm's law is a relationship between potential difference and current. It is current equals potential difference divided by resistance. Now, there are ohmic and non-ohmic materials where this applies. Ohmic materials are materials where Ohm's law applies, meaning that there's proportionality, while non-ohmic materials are materials where Ohm's law does not apply, meaning that the values are not proportional. Resistors are circuit elements that have resistance, and the definition of an ideal wire is a wire where the resistance is 0 ohms. The strength of an electric field in a resistor is represented by the potential difference divided by the length of the resistor. P bat, which is the rate of energy transfer, is defined as the change in potential energy divided by the change in time, which is also represented by the change in charge divided by the change in time times EMF. Now PEMF, which is the power delivered by a source of EMF, is just current times EMF. And the units of both of these power is watts. In a circuit, the sequence of energy transformations starts as chemical energy to potential energy to kinetic energy to thermal energy. What this means is that the battery's chemical energy is eventually transferred to thermal energy of the resistor, raising its temperature. The rate at which energy is transferred from current to resistor is the change in potential energy divided by the change in time, which is also the change in charge divided by the change in time times the potential difference of the resistor, which equals current times the potential difference of the resistor. And in a single resistor current, we can observe that the potential difference of the resistor is equal to EMF, meaning that the power of the resistor is equal to the power of the battery. The rate of power dissipation is the power of the resistor, which is equal to the current times the potential difference of the resistor, which is equal to current squared times resistance, which is equal to the potential difference of the resistor squared divided by resistance. It's time to move on to questions. The first question we're going to be analyzing is question 42. Question 42 reads, a 3-volt battery powers a flashlight bulb that has a resistance of 6 ohms. How much charge moves through the battery in 10 minutes? Well, according to the model, we see that we need charge, or Q. Now we know that the voltage is 3 volts and the resistance is 6 ohms. And according to Ohm's law, voltage equals current times resistance. Rewriting that, we get current equals voltage divided by resistance. If we plug in the values, we get 3 volts divided by 6 ohms, which is 0.5 amperes. And the next equation we use is current equals the change in charge over the change in time. And if you rewrite that, that's the change in charge equals current times change of time. So plugging in the values, we have the change in current equals 0.5 amperes times 10 minutes, which also equals 0.5 amperes times 600 seconds, meaning that our final answer is going to be 300 coulombs. The next question we'll be analyzing is question 51. The total charge a battery can supply is rated in mAh, the product of the current in milliamperes and the time in hours that the battery can provide of this current. A battery rated at 1000 mAh can supply a current of 100 mA for 1 hour, 500 mA for 2 hours, and so on. A typical double-A rechargeable battery has a voltage of 1.2 volts and a rating of 1800 mAh. For how long could this battery drive a current through a long, thin wire of a resistance of 22 ohms? Looking at the diagram, we see that we need time, or T. Ohm's law, once again, is voltage equals current times resistance. Rewriting it gives us current equals voltage divided by resistance. Plugging in the values, we have 1.2 volts over 22 ohms, which gives us 0.05455 amperes, which is equal to 54.55 milliamperes. Now the mAh rating is 1800 mAh. To get the time, we simply divided that rate by the amount of current. So we would have 1800 mAh divided by 54.55 mA, giving us a time of approximately 33 hours. The final question is question 61. A wire is 2.3 meters long and it has a diameter of 0.38 millimeters. When connected to a 1.2 volt battery, there's a current of 0.61 amperes. What material is the wire likely made of? For this question, we need the material. We use Ohm's law once again, which is voltage equals current times resistance. Rewriting gives us resistance equals voltage divided by current. Plugging in the values, we have resistance equals 1.2 volts divided by 0.61 amperes, which gives us an answer of resistance equals 1.967 ohms. The next equation we'll be using is resistance equals resistivity times length over cross-sectional area. Rewriting that multiple times gives us resistivity equals resistance times cross-sectional area over length. Now you plug in multiple values, we plug in the resistance. Since we have diameter, we have to find the area of the circle. So we would use pi radius squared. And we have the length, which is 2.3 meters, which gives us a final answer of 9.7 times 10 to the negative 8th ohm meters. And looking at a table, we could see that the material is iron. Thanks for watching.